Okay, in this video, we're going to talk about different ways that you will encounter representing molecules, and also ways that you're going to use yourself to represent molecules. So here are some of the most common ones. The two on the left are what I would classify as the most realistic representations of what molecules look like. The space filling is actually probably the most accurate. If we could blow up a molecule, this is what they would probably look like. I have a really hard time interpreting what these look like. And so, of the two more accurate representations, I like the ball and stick, because you can still see the geometry of the molecule, but it's much more clear what's going on in seeing who's bonded to whom and what the angles are and things like that. We've already seen Lewis structures. Oftentimes we'll use these partially condensed structures where, rather than writing the hydrogens coming off everything, right, we just sort of condense the hydrogens down. And so you might also see in a partially condensed structure, rather than writing this H down, we might just write CH. The condensed structures are things that you'll see, especially for simpler molecules. I personally have a hard time interpreting these, and so I don't use them much myself, but because we'll encounter them a lot in textbooks and other sources, it's good to know what they look like. And if you want help or practice with these condensed structures, I do have another video where we look at specifically drawing and interpreting condensed structures. The molecular formula has the least amount of information about all of these different ways of representing these compounds, but of course it's also the easiest to use. So some of the disadvantages of just using molecular formulas, and the reason we don't just use molecular formulas, especially organic chemistry, is because all of these compounds, isopropanol, propanol, and ethylmethyl ether, they all have exactly the same molecular formula. They're all C3H8O. But all of these compounds have very different properties, and that's why in organic chemistry we don't use the molecular formula very much, because it doesn't really give us enough information to know what the properties of that compound are. So that's why we tend to use some of these other ways of representing these molecules. Now, especially when we get to larger molecules, even drawing Lewis structures can be a real pain. It takes a long time to draw in all the carbons and hydrogens and everything. And so we very often use a shorthand in organic chemistry called the bond line structure. And we'll talk about how we convert a structure that looks like this into something that looks like this. But it has a number of advantages. One, it's a heck of a lot easier to draw. It's a lot faster, but it's also easier to interpret because there's a lot less clutter going on. And so we can see more clearly where the different functional groups are. So to interpret and to draw these bond line structures, what these structures represent is every time there's an endpoint or there's a corner in one of these structures, there's a carbon atom there, right? So this molecule has 1, 2, 3, 4, 5, 6 carbons. And so we have 1, 2, 3, 4, 5, 6 carbons. We do need, anytime there's a double bond or a triple bond, we need to be sure that we include those in our structure. So here there's a double bond between carbons 2 and 3, and so I have my double bond there. Or in this case, the triple bond, and I have a triple bond. Another nice thing about these bond line structures is that this zigzag format is actually fairly accurate in representing the angles in sp3 and sp2 hybridized carbons, where we know the bond angles are either 109.5 or 120. When we have sp hybridized carbon atoms, as we do in this structure, it's important to demonstrate that linear relationship for the sp hybridized carbons. And so when we have triple bonds, we don't use zigzags. We do want to show that those are linear. Now, so we know that the endpoints and the corners represent carbon atoms. The other simplification in these bond line structures is that we don't draw any hydrogens that are attached to the carbons. And so what we do is we use the octet rule and the fact that carbon always has 4 bonds to determine how many hydrogens there are. So for example, if I focus in on this carbon, right, it looks in the bond line structure, I'm only showing 2 bonds. Because I know carbon must have 4 bonds, I know that there must be 2 hydrogens attached to that carbon. And these guys on the end, right, there's a carbon here, I'm only showing 1 bond in the bond line structure, so that means I know that there must be 3 hydrogens. Especially later in this chapter and in other places, when carbon has a formal charge, it may not have 4 bonds, but we'll have to indicate that formal charge as either being negative or positive, and that will allow us to then determine the number of hydrogens, but that's a topic for a later video. So, when drawing and interpreting the bond line structures, sp2 and sp3 hybridized atoms in a straight chain should be drawn with the zigzag format, and then we have carbons on the endpoints and the corners. And same thing is true for the sp2 hybridized carbons. So I got to show the double bonds, but I can still use the zigzag format. For sp hybridized carbons, I've got to show that, right, I've got a carbon here and here that is sp hybridized, and I've got to indicate that it's linear. Right? I know there's a carbon here because the triple bond ends and then it turns into a single bond. So this junction between the triple bond and the single bond, I know there's a carbon right there. When drawing double bonds, you want to draw them as far apart as possible. For this compound, right, we've got the zigzag, we do the double bond to the O up, right? This is generally not preferred. For drawing single bonds, in general, the direction doesn't really matter. So, this compound is the same as this compound. Now, while we don't show carbons and we don't show hydrogens that are attached to the carbons, all heteroatoms, and heteroatom means just anything other than carbon hydrogen, we must show those. And we've got to show any hydrogens or anything else, or, well, any carbons that are attached to them we don't have to show, but any hydrogens on the heteroatoms we also have to show. So if I'm drawing the bond line structure of this, I've got 1, 2, 3, 4 carbons in a chain, so 1, 2, 3, 4. The oxygen's coming off carbon 2. I have to show that oxygen, and I have to show the hydrogen that's attached to the oxygen. Those aren't understood. And then sort of the cardinal rule, never draw more than 4 bonds to a carbon atom. Carbon can't expand its octet, so we'll never have more than 4 bonds on a carbon.